Welcome back. Today we will discuss arc length along a curve. One of the special features of smooth space curve is that they have a measurable length. This enables us to locate points along these curves by giving their directed distance s along the curve from some base point, the way we locate point on coordinate axis by giving their directed distance from the origin. Figure 1. Time is the natural parameter for describing a moving body's velocity and acceleration, but is the natural parameter for studying a curve's shape. Both parameters appear in analysis of space flight. To measure distance along a smooth curve in space, we add a set term to the formula we use for curves in the plane. Definition: the length of a smooth curve R of t is equal to f of t I plus g of t j plus h of t k, a less than or equal to t less than or equal to b, that is traced exactly once as t increases from t is equal to a to t is equal to b is L is equal to integral a to b square root of df by dt square plus dg by dt square plus dh by dt square dt. Question number 1. We usually take R of t is equal to x of t I plus y of t j plus z of t k. Then L is equal to integral a to b square root of dx by dt square plus dy by dt square plus dz by dt square dt. Question number 2. Just as for plane curves, we can calculate the length of a curve in space from any convenient parameterization that meets the stated conditions. The square root in either or both of equations 1 and 2 is mod b, the length of the velocity vector dr by dt. Hence, we have the length formula short form L is equal to integral a to b mod b dt. Question number 3. Example 1. Find the length of one turn of the helix. R of t is equal to cos t I plus sin t j plus t k. Solution. The helix makes one full turn as t runs from 0 to 2 pi. Figure 2. Using the length formula short form, the length of this portion of this curve is L is equal to integral a to b mod v dt is equal to integral 0 to 2 pi square root of minus sin t square plus cos t square plus 1 square dt, which is equal to integral a to 2 pi square root of 2 dt, which is equal to 2 pi root 2. This is root 2 times the length of the circle in the xy plane over which the helix stands. If we choose a base point p t naught on a smooth curve C parameterized by t, each value of t determines a point p of t is equal to x of t, y of t, z of t on C and a directed distance s of t is equal to integral t naught to t mod v tau d tau. Question number 4. Measured along C from the base point. Figure 3. If t greater than t naught, s of t is the distance from p of t naught to p of t. If t greater than t naught, s of t is the negative of the distance. Each value of s determines a point on C and this parameterizes C with respect to s. We call s an arc length parameter for the curve. The parameter's value increases in the direction of increasing t. Arc length parameter with base point p t naught is given by st is equal to integral t naught to t square root of x dash of tau square plus y dash of tau square plus z dash of tau square d tau, which is equal to integral t naught to t v tau d tau. Equation number 5. Example 2. If t naught is equal to 0, the arc length parameter along the helix R of t is equal to cos t I plus sin t j plus t k from t naught to t is s of t is equal to integral t naught to t mod v tau d tau using equation 4, which is equal to integral 0 to 2 pi square root of minus sin t square plus cos t square plus 1 square dt, which is equal to integral t naught to t square root of 2 d tau, which is equal to square root of 2t. Thus, s of 2 pi is equal to 2 pi root 2, s of minus 2 pi is equal to minus 2 pi root 2 and so on. Figure 4. Example 3. Distance along a line. Show that if u is equal to u1 I plus u2 j plus u3 k is a unit vector, then the directed distance along the line r of t is equal to x naught plus t u1 I plus y naught plus t u2 j plus z naught plus t u3 k. From the point p naught, x naught, y naught, z naught where t is equal to 0 is t itself. Solution. V is equal to d by dt of x naught plus t u1 I plus d by dt of y naught plus t u2 j plus d by dt of z naught plus t u3 k, which is equal to u1 I plus u2 j plus u3 k, which is equal to u. So, noting that being unit vector, mod u is equal to 1. S of t is equal to integral 0 to t mod v d tau, which is equal to integral 0 to t mod u d tau, which is equal to integral 0 to t 1 d tau, which is equal to t. Speed on a smooth curve. Since the derivatives beneath the radical in equation 5 are continuous, the curve is smooth. The fundamental theorem of calculus tells us that S is a differentiable function of t with derivative ds by dt is equal to mod v of t. Question number 6. As we expect, the speed with which the particle moves along its path is the magnitude of v. Notice that while the base point p of t naught plays a role in defining S in equation 5, it plays no role in equation 6. The rate at which a moving particle covers distance along its path has nothing to do with how far away the base point is. Notice also that ds by dt greater than 0, since by definition mod v is never 0 for a smooth curve. We see once again that S is an increasing function of t, the unit tangent vector t. Since ds by dt greater than 0 for the curves we are considering, S is 1 to 1 and has an inverse that gives t as a differentiable function of S. The derivative of the inverse is dt by ds is equal to 1 by ds by dt, which is equal to 1 by mod v, equation number 7. This makes R a differentiable function of S whose derivative can be calculated with the chain rule to be dr by ds is equal to dr by dt into dt by ds, which is equal to v into 1 by mod v, which is equal to v by mod v, equation number 8. Equation 8 says that dr by ds is a unit vector in the direction of v. We call dr by ds the unit tangent vector of the curve traced by r and denoted it by t. Figure 5. Definition. The unit tangent vector of a differentiable curve r of t is equal to dr by ds is equal to dr by dt by ds by dt, which is equal to v by mod v, equation number 9. The unit tangent vector t is a differentiable function of t whenever v is a differentiable function of t. As we will see in the next chapter, t is one of 3 unit vectors in a travelling reference frame that is used to describe the motion of space vehicles and other bodies moving in 3 dimensions. Example 4. Find the unit tangent vector of the helix r of t is equal to cos t I plus sin t j plus t k. Solution. V is equal to minus sin t I plus cos t j plus t k. Mod v is equal to square root of minus sin t square plus cos t square plus 1 square, which is equal to root 2. T is equal to v by mod v, which is equal to minus sin t by root 2 I plus cos t by root 2 j plus 1 by root 2 k. Example 5. Find the unit tangent vector to the curve x is equal to t square plus 1, y is equal to 4t minus 3, z is equal to 2t square minus 6t at the point t is equal to 1. Solution. The position vector of a point on the curve is given by r of t is equal to x of t I plus y of t j plus z of t k, which is equal to t square plus 1 I plus 4t minus 3 j plus 2t square minus 6t k. Then v of t is equal to 2t I plus 4j plus 4t minus 6 k. Hence, mod v is equal to square root of 2t square plus 4 square plus 4t minus 6 whole square, which is equal to 2 times square root of 5t square minus 12t plus 13. Therefore, t is equal to v by mod v is equal to 2t I plus 4j plus 4t minus 6k by 2 into square root of 5t square minus 12t plus 13, which is equal to t I plus 2j plus 2t minus 3k by square root of 5t square minus 12t plus 13. Therefore, at t is equal to 2, the unit tangent vector is t is equal to t of 2 is equal to 2i plus 2j plus k by 3. Example 6. Find the unit tangent vector at a point t to the curve r is equal to a cos t I plus a sin t j. Solution. V of t is equal to d by dt of a cos t I plus d by dt of a sin t j, which is equal to minus a sin t I plus a cos t j. Hence, t is equal to v by mod v is equal to minus a sin t I plus a cos t j by square root of minus a sin t square plus a cos t square, which is equal to minus sin t I plus cos t j. Example 7. The involute of a circle. Figure 6. Find the unit tangent vector of the curve r of t is equal to cos t plus t sin t I plus sin t minus t cos t j, t greater than 0. Solution. V is equal to dr by dt is equal to minus sin t plus t cos t I plus cos t minus cos t plus t sin t j, which is equal to t cos t I plus t sin t j. Mod v is equal to square root of t square cos square t plus t square sin square t, which is equal to square root of t square, which is equal to mod t, which is equal to t. Mod t is equal to t because t greater than 0. T is equal to v by mod v is equal to v by t is equal to cos t I plus sin t j. Definition. The involute of a circle is the path traced by the endpoint P of a string unwinding from a circle. In the above example, figure 6, it is the unit circle in the xy plane. Example 8. For the counterclockwise motion, r of t is equal to cos t I plus sin t j around the unit circle, v is equal to minus sin t I plus cos t j is already a unit vector. So, t is equal to v. Figure 7. Curvature. A frame of mutually orthogonal unit vectors that always travels with a body moving along a curve in space. Figure 8. The frame has three vectors. The first is t, the unit tangent vector. The second is n, the unit vector that gives the direction of dt by ds. The third is b is equal to t cross n. These vectors and their derivatives, when available, give useful information about a vehicle's orientation in space and about how the vehicle's path turns and twists. For example, mod dt by ds tells how much a vehicle's path turns to the left or right as it moves along. It is called the curvature of the vehicle's path. The number minus dB by ds dot n tells how much a vehicle's path rotates or twists out of its plane of motion as the vehicle moves along. It is called the torsion of the vehicle's path. Look at figure 8 again. If P is a train climbing up a curved track, the rate at which the headlight turns from side to side per unit distance is the curvature of the track. The rate at which the engine tends to twist out of the plane found by T and N is the torsion. Every moving body travels with a T and B frame that characterizes the geometry of its path of motion. The curvature of a plane curve. As a particle moves along a smooth curve in the plane, T is equal to dr by ds turns as the curve bends. Since T is a unit vector, its length remains constant and only its direction changes as the particle moves along the curve. The rate at which T turns per unit of length along the curve is called the curvature. Figure 9. The traditional symbol for the curvature function is the Greek letter kappa. Definition. If T is the unit tangent vector of the smooth curve, the curvature function of the curve is kappa is equal to mod dt by ds. If mod dt by ds is large, T turns sharply as the particle passes through P and the curvature at P is large. If mod dt by ds is close to 0, T turns more slowly and the curvature at P is smaller. Testing the definition, we see in the following examples 9 and 10 that the curvature is constant for straight lines and circles. Example 9. The curvature of a straight line is 0. On a straight line, The unit tangent vector t always points in the same direction, so its components are constants. Therefore, mod dt by ds is equal to mod 0, which is equal to 0. Figure 10. Example 10. The curvature of a circle, figure 11, of radius a is 1 by a. The parameterization for a circle having radius a is r of theta is equal to a cos theta I plus a sin theta j, and substitute theta is equal to s by a to parameterize in terms of arc length s. Note that if the radius of the circle is a and theta is the angle between two rays emanating from the center, then the length of the arc of the circle included between the rays is given by s is equal to a theta. R is equal to a cos s by a I plus a sin s by a j. Then t is equal to dr by ds is equal to minus sin s by a I plus cos s by a j, and dt by ds is equal to minus 1 by a cos s by a I minus 1 by a sin s by a j. Hence, for any value of s, kappa is equal to mod dt by ds, which is equal to square root of 1 by a square cos square s by a plus 1 by a square sin square s by a, which is equal to 1 by square root of a square, which is equal to 1 by mod a, which is equal to 1 by a. As a greater than 0, mod a is equal to a. The principal unit normal vector for plane curves. Since t has constant length, the vector dt by ds is orthogonal to t. This conclusion is using the result if u is a differentiable vector function of t of constant length, then u dot du by dt is equal to 0. Therefore, if we divide dt by ds by the length k, we obtain a unit vector orthogonal to t, figure 11, and is given in the following definition. At a point where kappa not equal to 0, the principal unit normal vector for a curve in the plane is n is equal to 1 by kappa dt by ds. The vector dt by ds points in the direction in which t turns as the curve bends. Therefore, if we face in the direction of increasing arc length, the vector dt by ds points toward the right if t turns clockwise and towards the left if t turns counterclockwise. In other words, the principal normal vector n will point toward the concave side of the curve, figure 11, because the arc length parameter for a smooth curve r of t is equal to f of t I plus g of t j is defined with ds by dt positive. ds by dt is equal to mod ds by dt, and the chain rule gives n is equal to dt by ds by mod dt by ds, which is equal to dt by dt into dt by ds by mod dt by dt into mod dt by ds, which is equal to dt by dt by mod dt by dt, equation number 10. This formula enables us to find n without having to find k and s first. Example 11. Find t and n for the circular motion r of t is equal to cos 2t I plus sin 2t j. Solution. We first find t. V is equal to minus 2 sin 2t I plus 2 cos 2t j. Mod V is equal to square root of 4 sin square 2t plus 4 cos square 2t, which is equal to 2. T is equal to V by mod V is equal to minus sin 2t I plus cos 2t j. From this, we find dt by dt is equal to minus 2 cos 2t I minus 2 sin 2t j. Mod dt by dt is equal to square root of 4 cos square 2t plus 4 sin square 2t, which is equal to 2. And n is equal to dt by dt by mod dt by dt, which is equal to minus cos 2t I minus sin 2t j. Now, it's time to summarize the session. In this unit, we discuss the idea of length of smooth curves and speed on a smooth curve. Also discuss the concept of curvature, which is very useful in the coming sessions. Before moving to the next class, here are some exercises for you. Find the point on the curve r of t is equal to 5 sin t I plus 5 cos t j plus 12 t k at a distance 26 pi units along the curve from the origin in the direction of increasing arc length. Find the length of the curve r of t is equal to root 2 t I plus root 2 t j plus 1 minus t square k from 0, 0, 1, 2, root 2, root 2, 0. Show that the curve r of t is equal to cos t I plus sin t j plus 1 minus cos t k 0 less than or equal to t less than or equal to 2 pi is an ellipse by showing that it is the intersection of a right circular cylinder and a plane. Find equations for the cylinder and plane. Write an integral for the length of the ellipse. Evaluation of the integral is not required as it is non-elementary. Hope you enjoy the session. See you next time. Till then, goodbye.